Okay, this video will try to help you do a Rankine cycle ease analysis, and what we'll focus on is the process. So just note that this process is applicable to all cycles. Think paper, then code. So in this particular example, we're going to deal with a standard Rankine. We're going to look at properties and efficiencies. We're first going to look at the turbine entry properties. So first, we're told that the temperature coming into the turbine is 1,000 degrees Fahrenheit, and its pressure is 600 psi. The exact state, well, it's a superheated vapor. We know that from a TS diagram. What's coming out of the turbine is some temperature. Initially, we're going to assign it to 80 degrees Fahrenheit. The quality is unknown. The condensate, we're going to assume, has a temperature that's 5 degrees cooler than the temperature coming out of the turbine or coming into the condenser. It's then pumped to 600 psia as it heads to the boiler. The efficiencies given are 90% for the turbine and 80% for the pump. The power produced is 1,000 kilowatts or 1 megawatt, a relatively small unit. We're going to seek to find turbine exit quality, the steam mass flow rate, and the thermal efficiency. We're going to use a technique called the VOS technique, an acronym that stands for visualizing, organizing, synthesizing, and evaluating. What's the best way to initially visualize this is to draw the cycle schematic. It's the classic schematic with proper labeling. State point labeling, component labeling. It also labels energy transfer into, out of, into, out of. This is a classic Rankine cycle, so it should look familiar. That completes sort of visualization and organization. We then try to synthesize. So we're going to pull in property relationships, conservation laws, entropy balance. We're then going to seek to evaluate this synthesis with either hand calculations or computers. We're going to seek to look at balances, order of magnitudes of values, and reasonableness. This part B basically asks, is what we've calculated believable? Okay, so now let's further synthesize, looking at state 1, P1 equals 600 psia, T1 1,000 degrees Fahrenheit. It is superheated because in a classic Rankine cycle, state point 1 is in the superheated region. In this region, we can calculate enthalpy and S as functions of temperature and pressure. Is this true inside the dome? No. We go over to T2, point leaving the turbine, entering the condenser. We only know the temperature, we don't know the quality. For 3, entering the pump, we assume that the temperature is 5 degrees cooler or 75 degrees Fahrenheit. We assume that the pressure is essentially equal to Psat at T3. That is a reasonable assumption coming out of a condenser. And then the quality of a saturated liquid is obviously 0. Next, now that we've sort of established the givens in 1, 2, 3, now let's go to some more equations. And in each case, what we're going to do is we're going to look at a component, like a turbine, and break it down in terms of work, efficiency, and properties. So in this case, the specific work of a turbine is H1 minus H2. We can get H1 from above here. H2 and W2 remain unknown. So if we were to enter this into EES, it would be one equation, two unknowns. Therefore, we need to keep coming up with new equations. The next logical equation is to use the thermal efficiency or the performance efficiency of the turbine, the isentropic efficiency of the turbine, as H1 minus H2 divided by H1 minus H2S. Remember, this value must always be less than or equal to 1. H2 and H2S are not known. However, H2S can be calculated from T2 with S2 equal S1. Therefore, H2 equals H1 minus A to T times open parentheses H1 minus H2S, close parentheses. As you can see, we're slowly building all the equations necessary to attack this problem. X2 will be equal to a function of T2 and H2, where H2 is calculated from over here. Looking at the overall system, we can write that the total work output is equal to the product of the steam flow rate times the net specific work, where the net specific work is calculated as the specific work output of the turbine minus specific work input into the pump, which we don't know. So we're going to define that as H4 minus H3. If you recall, that's basically from here to there on the TS diagram, where H3 can be a function of T3 x equals 0, since it's a saturated liquid. H4 will be a function of T4 and P, and we still have not used the isentropic efficiency of the pump. To get H4, we can use this relationship. Notice that the isentropic values are now in the numerator. We can obviously solve for H4, and H4S is calculated from a function of P1, comma, S4 equal S3. In other words, the pump isentropic enthalpy assumes that the entropy of S4 equals S3. Finally, we can look at the overall system thermal efficiency as the W net divided by Q in the boiler. This exercise of setting up all the equations for each of the components, from the pump to the condenser to the turbine and boiler, these equations can then be put into EES. And I'm going to show you that in the next video. What the beauty of after entering it into EES is now we can do parametric studies. We can study the impact of turbine exit temperature on the flow rate of steam and the thermal efficiency. We can determine the boiler temperatures and which has a greater impact on the thermal efficiency, the turbine or the pump. So in review, we make careful note on what is given. Turbine, condensate, efficiencies. We make careful note of what we're seeking to calculate. We apply a systematic approach based on this acronym of BOSE, of visualizing, organizing, and synthesizing. Finally, evaluating. We march carefully through each state point 1, 2, 3. This should all be done on paper prior to converting it into code. you can see that overall strategy in each component is an energy equation, an efficiency equation, and property equations. Each of those overall, or each component should take on that overall strategy. The overall system in terms of work net, obviously is interlocked. Finally finishing with the overall thermal efficiency, which would only be possible if we had each of the enthalpies. 1, 2, 3,